Hi to everyone, my name is Melina Scasserra, and I appreciate the opportunity to present this piece of research at the International Crosstie and Fastening Systems Symposium this year with the rest of my team, Carlos Aprile, Pablo Cocordano, Nicolas Beradi, and Pablo Tanaro. The five of us are civil engineers who graduated from the University of Buenos Aires some years ago and who currently work in Trenes Argentinos Infraestructura, a company that belongs to the Argentina Ministry of Transportation. In the academic field, Carlos and Nicolas are teacher assistants of the UVA Transportation Department, and I'm currently starting my PhD studies at the same university. The presentation, we talk about the use of under-sleeper pads and under-ballast mats to improve the performance of railway transition zones. Transition zones between ballast trucks installed over platform and over bridges have always required special maintenance works due to the early ballast deterioration and the differential settlements that can be observed in these zones of railway tracks. To date, transition zones are designed in Argentina to provide a gradual stiffness increase in the open track, in order to gradually match the stiffness of the track over the bridge. For the renewal of a bridge placed in a busy line where no other works are needed in the surrounding platform or tracks, the activities are generally organized during services cuts. Unfortunately, these solutions sometimes present an incompatibility between time necessary for soil treatment works and available working hours. In consequence, the quality of the works are not always the best one, which leads to rapid degradation of transition zones. The present study intends to analyze the performance of an alternative solution installed in a bridge as a trial, which offers a quicker installation time and solves the problem of differential settlements by using an elastic mat under the ballast, a UVM, placed over the bridge, and elastic pads under a sleeper, USP, to gradually decrease stiffness of the track. For this study, both materials were provided by Getzner throughout its national technical representative Rail Center by Boston. The technical solution presented here was designed considering the load, speed, and features of the track. The drawing shows the distribution of the under-sleeper pads along the transition zones and the bridge. On the other hand, the under-ballast mat is only installed on the deck of the bridge, which has a length of 12 meters. In order to evaluate the performance of the solution, two concrete bridges will be monitored, one which presents traditional transition zones, the bridge A, and another that uses the mentioned alternative solution, the bridge B. Both bridges are installed in the same track and have the same passenger and freight traffic. Then, the obtaining results for both bridges will be later compared in order to evaluate if the second option improves or at least equalizes the performance of the technical solution used in our country up to the present time. Both bridges were precasted in order to reduce in-situ works and, as a result, the time required for the installation. On the left-hand side, there is a picture of the soil treatment works needed for the installation of Bridge A. As you can see, traditional transition zones require a completely renewal of the surrounding platform and important in-situ efforts. For Bridge B, only a playtest was needed in order to check if the stiffness modulus was more than 80 megapascal. Moreover, as it can be seen on the right-hand side, USP and UVM were glued to the sleeper and to the deck before the installation, which undoubtedly reduced the time necessary for the activity. For the development of an integral analysis along a trial period, regular visual inspection of the transitions will be carried out, measurement of permanent vertical levels will be taken, analysis of ballast gradient and ballast falling index will be developed, and finally, measurements of vertical transect displacement at different locations of the transition zone will be analyzed. Moreover, the cumulative tonnage associated with railway services that monthly circulate along both bridges will be recorded in order to have an idea of the expected level of deterioration. To record the initial state, tests previously identified as A, B, and C were performed for transitions of both bridges in January 2020. Here we can see two photographs of the transition zones of bridge A and B. Both of them shows a recently constructed track. Regarding track geometry, permanent vertical levels for both rails, left and right, were recorded for the initial state of both bridges. As it can be seen from the plot, bridge A is located on a slope. Instead, bridge B, the one with USP and UVM, is located at the entrance of a transition curve. In consequence, we can see how the right rail goes up at the exit of the bridge in order to provide the required cant to the track. Regarding ballast breakdown, some authors indicated that an important breakdown of the ballast occurs at the exit of the bridge. Following this recommendation, two samples, one for bridge A and another for bridge B, were taken at 1.3 meters from the end of the deck. The ARIMA manual of railway engineering was used to define the depth of the sampling and to calculate the ballast falling index. As the manual says, a falling index smaller than 1 can be associated with a clean ballast. So we can conclude that both bridges present clean ballast. Finally, from the obtaining records in A, B, and C during this initial state, it can be concluded that both transitions seem to present similar characteristics, not being able to identify from the results which bridge present each of the technical solutions. 1 year after installation, during September 2020, tests previously identified as A, B, and C were repeated for transition zones of both bridges. Moreover, vertical transect displacement at different locations of transitions measured with photogrammetry and accelerometry techniques were analyzed. In this field, one of the most important aims of this test is to evaluate if the alternative solution solves the typical issues presented by traditional transition zones, such as the presence of hanging sleeper. Before starting, we analyzed the cumulative tonnage associated with passenger and freight services. The information was provided by the Traffic Control Department of Trenes Argentinos Operaciones. It is important to consider that 2020 was a special year with limited passenger and freight services due to COVID-19. In consequence, the cumulative tonnage resulted lower than the expected one. Then we carry out a visual inspection of both transition zones. From the photograph, it could be observed that there is no visual degradation in any of the analyzed transitions. Here, we can see the plot of vertical levels for bridge A. And here, we can see the plot for bridge B. If we compare permanent vertical levels measured in September with the ones obtained in January, it can be observed that top level for bridge B low down 5 millimeters more than levels of bridge A. We think that the crater settlements may be related with elastic deformation of USP and UVM that allows ballast particles to encrust on them. Regarding ballast quality, 2 more samples were analyzed, obtaining for both of them the grading and the fouling index. As it can be seen, the fouling index for both ridges, again, can be associated with a clean ballast. Finally, for the measurement of vertical transit displacement, photogrammetry and accelerometry techniques were used. Following recommendation of other authors, displacement were measured at the entrance of both transition zones. The main purpose of this test is to compare how the deflection of the track and consequently its stiffness change for both solutions along transitions. As it was mentioned before, it is important to evaluate if the alternative solution solves the typical issues presented by traditional transition zones, such as the presence of hanging slippers. Moreover, based on previous study, it will be also of special interest to analyze if the solution that combines the use of UEM and USP shows a better performance than those solutions where only UVM or USP were used. The accelerometry technique was implemented by Trenes Argentinos Operaciones, who provide the equipment and the know-how to develop the measurements and collaborate with the present study. We can see here a video recorded for Beach B, the one with USP and UVM, when the locomotive passed by. Here, on the left-hand side, it can be seen the location of the measured slipper for Beach A, and on the right-hand side, the obtained result for displacement in millimeters. Looking at the results, it can be observed that there is a difference between the results obtained using photogrammetry and accelerometry. Therefore, we think that more effort needs to be done in order to improve both methodologies. Analyzing the obtaining values, displacement for slipper located near the edge of the deck, cards 6, 7, and 8, are between 4 and 5 millimeters, while the displacement for cards 2, 3, and 4 are between 3 and 4 millimeters. Moreover, other studies have demonstrated that the relationship between rail displacement near the deck and rail displacement between 4.5 and 5.7 meters from the edge of the deck can have a good correlation with the performance of the transition zone. In this way, a radio of 1 can be associated with a perfect condition, and as the transition is degraded, the radio increases. In this way, we calculated the average of rail displacement for cards 6 and 7, the ones near the deck, and the average for cards 3 and 4, the ones located between 4.5 and 5.7 meters from the deck, obtaining a radio of 1.41, which can be associated with a good condition of track. Analyzing the results for Beach B, it can be observed that displacement for slipper near the edge of the deck are between 10 and 8 millimeters. On the other hand, displacement for cards 2, 3, and 4 are around 6 millimeters. As it was expected, transit displacement for Beach B are greater than those measured for Beach A, probably due to the elastic response of USP and UVM. Moreover, displacement for slipper near the bridge where the UVM is installed present greater displacement than those with only USP, confirming what was expected. Finally, we again calculated average 1 and average 2, obtaining a radio for Beach B of 1.58, which can be associated with a good condition of track. This test will be repeated in the following years for both transition in order to evaluate how this ratio changes as the gradation increases. In conclusion, the main purpose of this study is to evaluate if the alternative option that uses USP and UVM improves or at least equalizes the performance of the technical solution to date used in our country. From the works, it can be concluded that the installation of the Bridge B requires a shorter period of suspension of railway services, which is a great advantage when the time available is limited. In addition, the alternative solution has not shown at the date negative effects. However, the cumulative tonnage was very low during 2020. In consequence, the degradation of the track is not remarkable. More efforts need to be done in order to improve the accuracy of the displacement values obtained using photogrammetry and accelerometry. This study needs to be continued in the following years in order to evaluate how both transition zones perform as accumulated tonnage increases. For the future, it will be ideal to design a matrix that considers construction cost, time limitation for installation, expected accumulated tonnage, and maintenance cost, beside other aspects, in order to choose the best alternative for each special situation. Well, this is the end of our presentation. Many thanks for attending, and thanks Getsner and Trenes Argentinos Operaciones for your support.